Okay. Good morning, everyone. My name is Xijun. I go by Jeff, if that's easy for you guys. I'm an assistant professor at Texas State University. I joined Texas State in 2020. I graduated from Texas A&M in 2018. So today my talk is utilization of recycled material in concrete to promote sustainability. In the presentation, I'm going to talk about two projects we have done recently. One was using recycle. Both of the projects we did was using recycled aggregate in concrete. The first project we completed was a Textile supported project, which we used a recycled asphalt pavement or reclaimed asphalt pavement, which we'll call it RAP. And we use it as coarse aggregate replacement in concrete. The second one is we did a project for Oklahoma DOT. Actually, it was a field investigation. We looked at a concrete pavement section made with 100% RCA as coarse aggregate, and we evaluated the field performance. So the first project was from Textile and using RAP in concrete. Maybe you guys, I don't know, maybe some of you guys are not familiar with RAP. RAP is a reclaimed asphalt pavement. It's essentially demolished asphalt pavement waste, but it was processed as aggregate, and traditionally it has been widely used in HMA to replace both binder and aggregate. However, adding RAP in HMA, hot mix asphalt, has some problem, primarily due to the cracking issue. Textile had an interest in using RAP in concrete. In addition to Textile, Florida DOT, Illinois Tollway, Montana DOT, they all had RAP in concrete project. So that's kind of a background. So what we did is we collected a lot of RAPs from different Texas districts. We have a RAP from Houston, we have RAP from Bryan district, Amarillo, and San Antonio district. Then we did a lot of material characterization. We did an aggregate property test. We extracted binder and did a binder evaluation, like using PG grade system. We also did a particle shape and also stone mineralogy test. Then we put our RAP in concrete as aggregate replacement, and we primarily we only replace coarse aggregate with RAP, and based on volume percentage. We did some literature review. We found using fine RAP in concrete just did not work because it introduced a lot of strength reduction and caused a lot of workability issue. So that's why we only replace coarse RAP, and we only replace up to 40% by volume. Then we have 4 different mixtures, different type of RAPs, and in each type of RAP we replace 20% and 40% as coarse aggregate replacement. We used a typical Textile class P, which is paving material mix design, and we just modify the mix design by introducing RAP. The other objective of the project is to using RAP to try to serve as intermediate aggregate source to optimize aggregate gradation in RAP concrete. So that's why the reason behind it is that the asphalt industry use a little bit smaller aggregate size. So that's why in those RAP aggregate, they are smaller compared to the virgin coarse aggregate we use in concrete. So we were able to design dense graded RAP concrete by using RAP, which has more intermediate particle size. Then we did a lot of mechanical property tests, compressive strength, modulus elasticity, flexure strength, and also split tensile strength. We also did some pavement-related property tests because our goal was to design RAP concrete for pavement applications in Texas. So we did a coefficient thermal expansion, Poisson's ratio, and also we did some thermal property tests. We then evaluated the durability test property of a concrete made with RAP aggregate. We did a freeze-thaw resistant, We also did an electric resistivity to infer the permeability of the concrete, abrasion resistant. We also did a ring test to look at the cracking potential. In addition to those kind of conventional tests, I also developed a fracture mechanics-based test to evaluate the fracture properties of a wrapped concrete. So what I did is I developed a semicircular bending fracture test and to test the two primary fracture model parameters based on Dr. Shah's fracture mechanics theory. I just want to skip a lot of details because we only have 15 minutes. So for the results, what we found is that by adding wrap up to 40%, you can achieve similar fracture critical stress intensive factor, and the critical crack tip opening displacement value actually got improved a lot. And also you will have higher fracture energy terms. And with the statistic analysis verify those improvement was statistically significant. Then we also did a ring test. We actually did a mortar ring test. We also did a concrete ring test. For the mortar ring test, as you can see, by adding wrap here, you can significantly improve the cracking time, delay the cracking time. So the behavior of the wrap mortar is significant different from the control mortar. So you have a lot of stress relaxation, a lot of creep due to lower modulus also. So essentially the cracking time of the wrap mortar is about double of the original, the virgin mortar we tested. Like I said, I skipped a lot of details. I just want to conclude for the findings for the mechanical properties. By adding wrap in concrete, we had a reduction in strength, reduction in stiffness. However, we were able to minimize the strength reduction by utilizing optimized aggregate gradation. And also we found the strength reduction and modulus reduction was correlated with the asphalt content. So by controlling asphalt content, you can essentially design wrap concrete with adequate strength based on your requirement. We also did some microstructure analysis by using X-ray CT microscope, and we found the asphalt layer is a weakness point. So that most of the time the cracking passes through the asphalt layer. So that's also confirmed why we can control the asphalt content by controlling the strength. Durability, we did not find a lot of durability issues if you just use 40% wrap. And we also propose some method can help select the best wrap for concrete applications. So essentially, we just need to control the gradation. We prefer lower asphalt content, but we also have method to design the wrap concrete with adequate strength based on the asphalt content. Based on the fracture properties, we found wrap concrete has equivalent fracture toughness compared to the control sample. It has higher ductility, higher fracture energies, and for the cracking resistance, we found the wrap mortar sample developed delayed cracking time, and the possible reasons are the lower modulus, higher fracture energies that we tested, and also viscoelastic stress relaxation. So our conclusion is that we don't think wrap-based cementitious material are inferior materials. If we design them properly for some applications, for example, if we want to high cracking resistant, they can potentially be used for some special applications. We want to acknowledge Textile to support this project, and Dr. Arnaud Mukhapadhyay was PI, and I was a PhD student working on this project. All right, the second project, I probably running out of time, so I will just do it very quickly. That was a long-term performance evaluation of concrete pavements containing RCA in Oklahoma. So I think everyone knows the benefits of using RCA in concrete, so that's why I did not have any background. A little bit background about this particular project. In 1980s, Oklahoma DOT already built 2 sections containing 100% RCA as coarse aggregate replacement, and it was JPCP sessions, and the other was CRCP session. Both sessions have control sessions, so which provide a very good opportunity for us to evaluate, because we can directly compare RCA concrete performance with control performance. One was on I-30 and I-40, and the other was on I-35. We went to Oklahoma City, and that where the few sections was at, and we did a visual inspection. We found there was a significant amount of longitudinal cracks on I-40, which was JPCP, but for the CRCP section, which was on I-35, looks very well. And we did the course, we get samples, we look at the bonding between the concrete layer and the base layer. We found the CRCP section, the bonding was really good, which is a picture over there. But for the JPCP, they use a soil base, and it was really weak. And we found a lot of debonding issues. Then we did a FWD test to evaluate the structural performance of the concrete pavements. We developed some theories based on my advisor. So we evaluate the equivalent thickness, base coefficient of friction, differential energy, and load transfer efficiency of both 2 concrete pavement sessions. Again, I skipped a lot of the results. So major conclusion are for the I-40 JPCP RCA session had lower performance compared to the control session, but for the I-35 CRCP session, the control and RCA session were essentially very comparable. We also had data from Oklahoma DOT. They did a distress survey, and we also compared the survey data with our structure analysis, and we found they match well with each other. And we also did some mechanical testing using the core specimens. We found RCA concrete has lower modulus elasticity and split tensile strength, which match well with the literature review. We also found RCA concrete, one sample showed higher compressive strength compared to the control sample, which also was found in the literature review. So that was very interesting. We also did some petrographic study by looking at the microstructure of the concrete, and we found the crack always passed through the reclaimed mortar, which also verified the reclaimed mortar was a weak point in RCA concrete. Findings from Oklahoma concrete pavements, RCA concrete, we had a reduced modulus elasticity and the tensile strength, but we did find that one specimen had improved compressive strength in the field. And reclaimed mortar was a weak zone, and the crack can pass through it. And we found the lower performance for the JPCP session, but for the CRCP session, the performance was comparable between the RCA and the control. The reason behind why the CRCP session had a similar performance compared to the control is that it has stronger base, and also we thought the CRCP is stiffer and it can prevent base from erosion better compared to the JPCP, which was built on a soil base, which was really weak. Again, I want to thank Oklahoma DOT and my former advisors, Dr. Dan Zollinger and Dr. Norm Mukherjee. And we published a lot of papers. For the wrap concrete, I listed a few papers. If you want to look at the details of the results, you feel welcome to look at them. For the RCA concrete, we also have a few papers. That's it. Thank you so much. If you have any questions, I'm open to questions, or you can send me email. Thank you so much. Yes, please.
Yeah, great presentation. Thanks. I'm curious about using the wrapping concrete. So, obviously, the structural concrete is going to be a challenge. I mean, strength is going to be strength homogeneous is going to be a problem. But I guess we thought about this a lot for payments. There's been a lot of work done in this trying to use it in payments. Is there some advantage maybe because it can provide some flexibility? I know in payments we're always worried about deep cracking. You see some advantage because actually this asphalt may provide a little bit of flexibility and without cracking. That's how we see asphalt payments in general.
Right. Yeah, that's a good question. So we think, yeah, we actually think it's a good material. First of all, it had lower modulus and high viscoelasticity, high stress relaxation. So the cracking width, especially for CRCP, because CRCP will have cracks. So the cracking width will be lower. That's also based on our payment ME analysis. We found the crack width was lower. That's all due to the creep. And also for the strength, actually for payment design, we look at the fracture strength more. So our results show that the fracture strength reduction was much lower compared to the compressive strength reduction. So that's why if you just add maybe 20% wrap or 40% wrap, your fracture strength reduction, you can keep it within 10%. So I don't think that's a big concern for the strength perspective. And also our fracture mechanics results show that the fracture toughness was similar. You have higher ductility, maybe higher fracture energies. So based on the fracture mechanics theory, if you look at a big scale or intermediate scale structure, you need to look at a fracture mechanics theory instead of strength criteria. That's the size effect proposed by Bassan. So that's why also some few sections like Illinois, they did some few sections. Florida is trying to do a few sections. Hopefully they can also show some good results. So I don't think it will have a lot of concern regarding structural performance. My concern might be the surface abrasion. Those things maybe wrap will pop out. Those things might be a little bit concerned, but for the strength, I don't think that's a concern. Thank you so much. And I think that flexibility can add some values for concrete payments by control the cracking. Thank you.
We have one question from the online audience. Asked, have you tested more than 40% of wrapping the mix? Is 40% the limit?
No, we did not add a lot of more than 40%. The reason behind it is we did a lot of literature review. Illinois Tollway, they did a test at University of Illinois. They did a 40%, 50%. So that's why we want to control 40%. We do not want to introduce a lot of strength reduction, and we want to be realistic for our testing plan. But Montana State, I think they did 100% coarse wrap, and they even add fine wrap. So yeah, it can work if you design it properly. Yeah.
Yeah, just a comment on the fracture energy.
Yes.
The half cylinder notch test is being done by several tests. It's known that it's really not reliable for small or bigger than only one of the time behind the side. But I think we really want to get something or this to see if there is a different fracture problem. We need at least the classical 6x6 notch. You might see something there. I'm not sure, but I think it would be a good idea. That test is going to be not very reliable.
Yeah, thank you so much. Yeah, I also received that comments when I submitted my paper to some journals. The method was published at the CCC. If you are interested, so what we did is we did it's different than the asphalt testing method. So we did loading and unloading, then reloading, so that you can use non-linear. So it's not a linear elastic; it's non-linear.
Very well.
Okay. Yeah. ligament, we also have some comments. I think, perhaps we need to have higher, bigger specimen that can help. That's a good question, good comment. Thank you so much.
Oh, well, let's go on to the next.
Thank you so much.